Hi, my name is Fredrik Sandblom from the NX marketing team. Welcome to this how-to session on how to create an assembly in NX for the first time. In this session, we will be introducing you to the NX assembly application and the tools that goes along with it for you to get a quick start in NX assemblies. Assuming we have the files organized on the file system and the crucial NX assembly settings in place, let's dig into the easy work of assembling some of the parts for the final product of the gearbox you see on the screen. Here displayed together with the actual power unit in the form of an electric motor. In the following example, however, we will be focusing on the gearbox only. To start off with, we first close the example that we have loaded and start fresh by creating a new part. As we are creating an assembly, make sure to select the assembly template part, as this contains specific settings optimized for assemblies. We navigate to the specific folder where we want the part saved and to keep our work organized. As the project folder here has the same name as the intended assembly, we simply copy the name and add the suffix ASCII to identify it as an assembly. We note that the assembly tool is invoked automatically doing this operation. But as we really want the first part we add located and positioned absolute in the assembly, we close this tool and open the Add Component tool instead. To select the part we want to add as a component to the assembly, we navigate to the project folder containing the specific part. As the angled gearbox housing is the essential part here, to which all other parts are attached to, this will be the first part to be added. We ensure that this part is added in the absolute position. This ensures that no accidental rotations are included. However, the absolute origin of the part does not align with what we consider to be the correct origin. So we move the component to where we want it positioned. We do this by first toggling the move handle only on and move only the positioning coordinate system to align with the center of the incoming hole. We then turn the move handle only off and set the coordinates to match the origin. We OK to confirm, and we then receive an option to add a constraint that will fix this part to its current position in the assembly. However, as we want to get an understanding to the fix constraint, we choose here to not add the fix constraint. So, to get an understanding to why the system offers to fix the first component and make it non-movable within the assembly, we evoke the Move Component tool and use one of the drag handles to move it around. We can now see that the component we selected is moving freely within the assembly. To prevent this, we cancel the modification we just did with the Move Component tool, and we manually add the fix constraint to the first and crucial component here. Having a look to the positioning column in the assembly navigator, we can also see that the component is fully positioned with the fix constraint represented in the column. Time for to add the next component, and as we added the project folder as a palette to the resource bar here to the left, we can now very quickly navigate to the part we want to add to the assembly as a component. Here we simply identify the part on the palette and then simply drag and drop it into the graphical window. This procedure immediately evokes the auto align option, and we can directly start selecting the geometry pairs from the two components that we want to constrain relative each other. We select both the cylindrical faces of the two components and align the incoming axle mount to the cylindrical corresponding hole in the gearbox housing. We note as the align constraint is fulfilled by the constraints, the component moves to the aligned position. To continue, we now tell the system to align the inner flat face of the incoming axle mount to the outer flat face of the gearbox housing, and the component is moved to its updated aligned position. Still, within the Auto Align tool, we can easily check if a component is free to move in any way, or the so-called degree of freedom. To do this, we simply hover the component we want to check for degree of freedom, press and hold the left mouse button, and move the mouse to see what moves. Here we can see that the incoming mounting plate still can rotate around its own axis. We can also utilize the Show Degree of Freedom and then select the component to check. The symbol shows the degree of freedom. The symbol is also temporary and goes away with the refresh of the screen. As where possible and in general, the rule of thumb is to fully constrain components. We still need to constrain this final degree of freedom. We will be doing this by aligning the bolt holes to each other, ensuring the correct position of the component. So, to do this, we simply evoke the Auto Align tool and select the clearance hole on the incoming axle mount, and then the matching bolt hole on the gearbox housing. The component automatically repositions itself to comply with all our constraints that we have applied to it. To double check, we here once again evoke the Show Degree of Freedom. We select the component and notice that no degree of freedom symbol shows up. And so our component is now fully positionally constrained, and we can no longer accidentally move it. We can also validate the position by checking the position column in the assembly navigator. Here we can see the status of the positioning of the components in the assembly. And here we see that the incoming axle mount is fully constrained. So all good here. Looking in the graphical window, we can see that there are small blue symbols that have shown up. These are the assembly constraints that we have been creating. You can select them in the graphical window directly and interact with them should you like. You can also find them in the Assembly Navigator under the Constraints node, where you have the ability to interact and edit them as well. If you think they are cluttering the graphical screen, you can turn them off under the Constraints node by right mouse button click on top of them. So, now that we are familiar with adding components from a known library, we also want to have a look on how to add what is defined as a standard part. We therefore navigate to the Reuse library and to the sub-library containing the part that we need. With previews of the standard parts, they are easy to identify. Note that if our library is packed with parts, you can do a search at the top of the Reuse library tab for easy finding. Once we have located the part, here a ball bearing, we need to simply drag and drop it into the graphical window. Once added, we are immediately presented with the Auto Align tool. We select the cylindrical face from the incoming axle mount and the ball bearing, and then let the system align to our requirements. We continue by defining the seating faces on the ball bearing and the incoming axle mount. And again, let the system align to our requirements. Checking the position status of the ball bearing component we just added in the Assembly Navigator shows that it is only partially positioned. Checking with the Show Degrees of Freedom tool reveals that the component can rotate around its own axis. However, when it comes to, for example, cylindrical shaped parts like ball bearings or bolts, there is no need to lock the rotation as this is not really adding value to the assembly, and it can therefore be accepted to be partially positioned. Now, depending on your view settings, it can be difficult to really see the resulting temporary symbol from the Show Degrees of Freedom operation. To improve, you can switch the emphasis setting, See Through All, and things will be much clearer. The shortcut F5 refreshes the screen and the temporary symbol disappears. More standard parts needs to be added. The ball bearing needs to be locked in place with a retainer ring, and so we navigate to where we find standard parts in the reuse library. We drag and drop the retainer ring of choice into the graphical window. The cylindrical radial seating face on the retainer ring and the counter face on the incoming axle mount are selected to align the radial position. The flat face on one side of the retainer ring and the counter face on the incoming axle mount are selected to align the axial position. As this is a cylindrical part, we do not bother about locking down its rotation, and so this component will be partially constrained, which is just fine. As this gearbox is filled with oil, we need to add a radial seal. This is a standard part as well, and we again find it in the standard part library. Drag and drop adds it to the assembly, and we use the auto align tool to position the component, just like we did with the ball bearing we just added. Now, to keep the radial seal in place, we need to add another retainer ring. Of course, we can add it from the reuse library just like we did with the other one, but as it is already in the assembly, we can easily get it from there. We simply select the component that we want to copy and evoke the Move Component tool. Here we toggle the copy option on and simply drag the component to a new place using the positional drag handles. Now, this will create a copy of the component, but it needs to be positioned with constraints. If you would like to reuse the constraints that you have already created, you can simply do a copy and paste operation. We right mouse button click on the retainer rings in the assembly navigator and choose Unpack, as there are two of them and we need to pick the one we added last. We delete it so that we can demonstrate how to use the copy and paste option. To copy a component, you can either choose it directly from the graphical window or from the assembly navigator. In this case, we hover the retainer ring component, right mouse button click and select copy. We then hover the assembly to where we want to paste the component. Right mouse button click and select paste. As the component we copied had positional constraints attached to it, these are carried along. We can choose to delete them if we do not like them and wish to create all new constraints. However, in this case, we will reparent the constraints that now are missing the counterpart for the two constraints listed with a red asterisk. Selecting the constraints of interest from the list in the menu shows the constraint entities highlighted in green in the graphical window that needs a counterpart to satisfy the constraint. The first one shows a flat face on the retainer ring that needs a counterface on the part to constraint 2. And the other constraint is the axial alignment that needs a cylindrical counterface or axis. We start satisfying the axial alignment and select the cylindrical counterface. We continue by selecting the planar alignment. With the planar face of the retainer ring selected, we proceed to select its matching planar face on the groove it is to be fitted into. However, the retainer ring ends up not quite in the correct position. This is easily addressed by reversing the direction of the constraints. As both constraints here have a directional sense, we need to change the direction of both of them, otherwise they would be in conflict with each other. Now that the constraints are satisfied and showing the green tick in the list of the menu, we can confirm and accept the new position. To speed things up a bit, we will now jump ahead to where the whole transmission from the electric motor to the gearbox is fully assembled and where it needs to be bolted on to the gearbox. We will be doing this so that we can demonstrate the use of pattern component. We start by locating the per specification required countersunk hex bolt in the reuse library, and when located, we simply drag it into the graphical window. We align the center axes of the bolt and one of the holes, and finish off with aligning the flat face of the head of the bolt to the flat face it is seated to. As this bolt resides in all of the fixing holes for the transmission assay, we utilize the pattern component. As the first bolt is mounted to a hole on a part that contains a hole pattern, the system recognizes this and automatically patterns the bolt. Awesome! As this was the final piece in this demonstration, I would like to summarize what you have seen. You have seen how to create a new assembly file using the proper template while creating an assembly. This is important as the assembly template contains important settings for an optimized behavior of your assembly in NX. We utilized a folder set up as a palette and where you can utilize the drag and drop procedure to easily add components to an assembly. We defined constraints to components as we added them, and we noted that the first component we add is generally locked in place by utilizing the fix assembly constraint. In addition, we frequently use the auto align tool. That is a really neat and quick tool when constraining your assembly. The reuse library were used in combination with drag and drop to easily add standard components. As components needs to be properly constrained in the way they behave in the assembly, we noted that we are able to check if and how they can move by using the Show Degrees of Freedom tool. To create multiple copies of components in the assembly, we used both the Move components as well as Copy and Paste option, where the latter allows for to reuse already defined constraints. We demonstrated how to handle conflicting constraints and to solve similar situations. And finally, we had a look at how to quickly create a component array and reuse the pattern from an existing component in the assembly. This concludes this how-to session on building an assembly for the first time. And with that final statement, I would like to humbly thank you for your time and attention.